All right, so let me change my pen color. Oh. All right, yeah. Yeah, so at this point, so let me refresh your memory a little bit. The Fibonacci problem, the linear recurrence relation, we have a full name for it. So here, this long name, the full name for that type of equations. Second order linear homogeneous recurrence relation with constant coefficients. Yeah. All right, so now to solve that, yeah, so here let's look at the main part of the equation. Yeah. At the beginning, let us ignore the initial condition part. Yes. Because this is the main equation. Yeah. So first, let us find a solution satisfying the main equation, main recurrence relation. Yeah. After that, then we try to see if we can find one special solution to satisfy the given initial condition. Yeah. So we use those two steps. All right. The first step, the biggest step, yeah. How to solve. So here, I give you the whole process of problem solving. Yeah. So try to, so you try to follow my thinking. Yes. Try to follow my story. Yeah. Yeah. All right. At the beginning, we need to understand the problem, right? Yeah. So when we understand the problem, we want to take some special view. Yeah. So the special view here means you try to find some special property in the given equation. Yeah. So this part usually not very easy. So you need to have some experience. Yeah. So the more experience you have, the better you can do in this step. Yeah. All right. So here, now, what I put here is consider a sequence, A sub k sequence. Yeah. Yeah. Because if we can find a solution for this equation, you get a sequence of numbers, right? Fibonacci numbers. You can treat Fibonacci numbers as a sequence of numbers. Yeah. Here, we are looking for a sequence of numbers satisfying a given equation. Yeah. So that's the special view we take. Yeah. Yeah, not very special. Actually, it's a very natural view, right? It's a natural view we take. Yeah. But when we take this natural view, yeah, the first thing we need to do. Remember last time, I remember when we solve some problem, I said in problem solving, making a good guess is very important. You need to use your imagination to make good guess. Yeah. And a very brave guess. Yeah. That part. So that part you need to have some creativity. Yeah. So that part you really need to have some creativity to make a smart creative guess. Yeah. So here we need to do that. Okay. All right. So but another thing, so here another point I want to point it out is experience is very important, because when you make a guess, you need to base on your experience. You need to base on your experience. Now, if you do not have much experience, you cannot make a good guess. Now, because your guess comes from nowhere, right? So your guess has to come from your experience. So that's very important. Yeah. So here, let's look at our experience. Yeah. What we have learned so far, that is our experience. Okay? So what do we have? Do we have some related situation that we did before that we can borrow from our old experience? We didn't do much like this before, right? But we did something like this before. Not zero. So we did something related before. Yeah. So what's that? Recall, we solved the simpler version of linear recurrence relation in the problem, Tower of Hanoi problem. Think about that. That's our experience. The Tower of Hanoi problem. Yeah. So here we need to borrow our experience from that problem, Tower of Hanoi problem. Okay? Yeah. All right. So let me show you. Yeah. So that experience is very useful here. Yeah. Do you still remember the solution? So the Tower of Hanoi problem, we have a first order linear recurrence relation. Right? Yeah. So here, if I write the equation again, so that is relation. C of m equals 2 times C of m minus 1 plus 1. Yeah. That is the linear recurrence relation. It's a first order. Yeah. Although first order, second order, different, but at least they have some co-relationship, right? At least they have some co-relationship. Yeah. So we want to, explore that co-relationship here. Then let's think about what's the solution of this linear recurrence relation. Yeah. Anyone still remember a little bit? Yeah. All right. So here, let me write it out. C of m equals 2 to the n minus 1, right? That's the solution. 2 to the n minus 1. Okay? Yeah? All right. Then, what can we borrow from the solution? Yeah. What kind of guess we can make from the solution? Yeah. Our question. Yeah. Yeah. Because here, our goal, we want to make a good guess for the solution sequence. Suppose this is the solution sequence. Yeah. And what specific form should we take for the solution sequence? That's our goal. Yeah. But from this solution, can we get some idea of for the solution sequence? Yeah. 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 Try to yeah, because this form, yeah, we see some form here, right? 2 to the n minus 1. Yeah. But there is a minus 1 part. Yeah. Remember, the minus 1 is related to the non-homogeneous part, that plus 1, non-zero constant. Yeah. In our solution, the first step, we try to eliminate non-zero constant term, and we introduce a new function called a d function, right? D of m equals C of m plus 1. After that, then the non-zero constant is gone, so we get equation d of n equals 2 times d of n minus 1, right? Yeah. Recall our solution steps. Because we want to borrow some useful idea from our old solution. And this one is a homogeneous version, right? And our current equation, this is a homogeneous equation. See? Yeah. homogeneous, yeah, then they should share some similarity, right? Both homogeneous linear recurrence relations, they should share some similarity in their structures, in the solution structures. Yeah, that's our understanding, okay? Yeah. So that's how we understand this current problem. Yeah. All right, and we know this D function has the solution 2 to the n, and there is no minus 1 part. Okay? The minus 1 part, later when we go back to C function, we do the minus 1 correction. Okay? All right? But if we only consider the homogeneous case, then we do not need to minus that 1. Okay? All right. So here you can see the solution has the form, some number here, it's 2, some constant number, 2 to the n. This structure, 2 to the n. All right, that's for the linear recurrence relation. Here, the linear second order recurrence relation, can we borrow the same structure here? When we make a guess, to represent our solution, can we use the same structure from the first order linear recurrence relation? That's a natural thinking, right? That's natural thinking. Yeah. All right. Yeah. So the guess of the structure based on our Tower of Hanoi problem, that experience, we make this guess. How about we assume the sequence takes this power function. Yeah, this is a power function, t to the k, power function. Okay, what's that t? It's unknown. We don't know what's that t. Okay, what's that t? Yeah. But we want to find a sequence t squared, t cubed, t to the fourth, and so on. Yeah, that sequence. Yeah, people also call it geometric sequence. Yeah, yeah. We want to try. This is a guess. We want to try. Is it possible to find a solution with this structure that satisfies the given recurrence relation? See? Yeah? Yeah. Yeah. It comes from somewhere, right? Old experience. It's not from nowhere. Yeah. It's not magic. Yeah. It's not magic. Yeah. It comes from our old experience. Yeah. All right. So now let's plug in. Yeah. Let's assume. So here we make assumption. Our assumption is a sub k equals t to the k. That's our assumption. With this assumption, we want to plug in this form into the original recurrence relation. Now, okay, without considering the initial condition. Yeah. So we will take care of that part at the end. Yeah. Yeah. All right. Yeah. So let's try. Yeah. After we plug in, we get this equation. T to the k corresponding to a sub k at the left-hand side of the original equation. Yeah. So t to the k equals t to the k minus 1 plus t to the k minus 2. Yeah. This new equation, do you feel simpler? Do you feel simpler? Comparing with our original equation, yeah, under our special assumption or special guess, it is much simpler. This equation is much simpler. Let's do simplification. Cancel some common factor out. sides. Cancellation equation. Okay. Yeah. All right. Yeah. So the lowest term, we treat the lowest term, lowest degree term. So that's the lowest degree term. This one, we can do division by this term, both sides, to get a simplified version, t squared equals t plus 1 after the cancellation. Much simpler. Yeah. So this is a quadratic equation, right? Quadratic equation. And we have confidence to solve any quadratic equation, right? Because we have the quadratic formula. Yeah. And but this quadratic equation, do you feel it looks familiar to you, this quadratic equation? Have you seen this before? This quadratic equation before? Yeah? Remember the golden ratio? The golden ratio, how do we find the golden ratio? The golden ratio comes from the same quadratic equation, right? Yeah. So let's do it again. Yeah. The way we find the golden ratio. Yeah. All right. So by the quadratic formula, we have two solutions, not one. Yeah, two solutions. T1 equals golden ratio. This number is the golden ratio. 1 plus root 5 over 2, golden ratio. But there is another solution. T2 equals 1 minus root 5. Yeah. Remember the first time when we solved this quadratic equation, because we want to find the golden ratio, and at that time we know the golden ratio cannot be negative number, right? So we drop the second negative solution. But here, this t, t1, t2, this t, because what's the meaning of this t? This t, just any number, such that satisfy the original recurrence relation, right? We do not mean, or we do not assume t is the golden ratio, right? Yep. So t so t could be negative. Yeah. Some students may argue, yeah. So because your goal, you want to find the positive, so you should take the positive solution. Yeah. So if you think in that way, so let me clarify it. Okay? Yeah. So here, if your argument is, since our goal, we want to find a formula for the Fibonacci numbers, and the Fibonacci numbers, other than the first one, 0, they are positive. Or we can say Fibonacci numbers, they are non-negative numbers. So for that reason here, the t should not be negative. If you make that argument, let me give you the further explanation. So the t, when we use this t form, our goal is we just want to find a solution of the original equation. We do not mean the solution has to be Fibonacci number. No. So here, let's forget about the Fibonacci numbers at this point. We just want to find a solution, whatever solution it is. Okay? Any solution. Non-Fibonacci number solution, we still want to take it. We want to find the solution of the original equation. Okay? Now, the Fibonacci number solution, we delay it at the end. Okay? We delay the Fibonacci number solution to the end. Yeah. So at this point, we want to find a general solution. Yeah. So you can think in this way. Our goal here, we want to find a general solution that satisfy the given recurrence relation. Okay? The general solution, because it's very general, it will contain Fibonacci numbers. Fibonacci numbers will be treated as a special solution. Yeah. But here we are looking for a general solution. Yeah. All right. So for that reason, negative t is allowed. Negative t is allowed. That means the T2 option, the second solution using negative t number T2 should not be dropped. We should keep it. So we should keep the T2 solution. So after this point, we have two solutions. T1 solution and a T2 solution. Two solutions. Yeah. All right. Yeah. So after this discussion, yeah. So what do we have so far? We have two special solutions. Yeah, they are special solutions. T1, T2, they are special solutions. Okay, all right. Yeah. So then let us write it out. Our two special solutions to the original recurrence relation. The first special solution, when we plug into the original recurrence relation, we get the first equality. Yeah. It must be correct, right? It must be correct. Yeah. Yeah. Because we solve the equation to find it. Yeah. And T2, if we plug in T2 special solution, we get a second equality. Yeah. And we know it's also correct. Yeah. So these two equalities both correct. Yeah. And here we have two special solutions of the original recurrence relation. Yeah. So here, let me write it again. This is original recurrence relation. Yeah. Yeah. All right. Yeah. So that's that. Next, we want to find a general solution. With these two special solutions, can we find a more general solution? Yeah. Because we know these two special solutions, they have no way to be the Fibonacci numbers, right? Yeah. Yeah, because these two special solutions, they are both non-integer solutions. They are both non-integer solutions for the original recurrence relation. And we want to find integer solutions. The Fibonacci numbers are integer solutions. Yeah. So our next step, we want to look for a more general representation for the solution. Yeah. All right. Yeah. And definitely, these two non-integer solutions, they do not satisfy the initial condition. Yeah. Yeah. So we need to solve the next problem. Yeah. Yeah. Integer solution problem. That problem. Okay? All right. So next, the question. Yeah. Our next step. How to use two special solutions without the initial condition to get a new solution with the initial condition. Yeah. If we can answer this question, then we are done. Right? We solve the problem. Yeah. Yeah. All right. So the next question, we need to do another creative step. Another creative step. To do what? Yeah. We have something in our pocket, right? Yeah. At this point, we have something in our pocket. So that is two special solutions. Yeah. Very useful. Yeah. So we want to use these two special solutions to construct a new general solution. That's our new goal. New goal. Use two special solutions to make a new general solution. Yeah, that's our new goal. Okay? Yeah. So the question is how to make it. How to do the construction. Yeah. Construction work here. Okay? All right. So is there a special way to combine two solutions? Yeah. So basically the new general solution is just a special way to combine two special solutions. The question is how to combine two old solutions. Think about that. Yeah. How do you combine two old solutions to make a new solution? Yeah. That's an important question we need to answer at this point. Okay, all right. Yeah. So let's go to the next slide. Combination way. Yeah. So here we need to find a reasonable combination way to combine two old solutions. So here, there is a way called a linear combination of two variables, that concept. So here, there is a concept called a linear combination concept. Yeah. This time, we need to use a special property of the equation. So the equation property, this equation, remember, there is a property called the linear property, right? This equation is a linear equation. Linear equation has the linearity property, right? Linearity property. So here we want to take advantage of the linearity property to combine two old solutions. So how to take the linearity property? So linearity property. So we can use this linear combination concept to take advantage of the linearity property of the equation. Yeah. So what's the meaning of linear combination of two variables? It has this form. ax plus by. Capital A, capital B are two constant, not variable. So they are two constant numbers to be determined. So here we don't know those two numbers. Yeah. They could be any two numbers. Yeah. But x and y, they are two variables. Yeah. So how to combine two variables, x and y? There is a concept called a linear combination. It takes this specific form. ax plus by, we called this form the linear combination of x and y variables. Yeah. So this place, can we use the linear combination of two old solutions to form a new solution? That's the point. Okay? Yeah. All right. Two constant AB, we will determine A, capital B later. Okay? So here we just assume there are two constants. Yeah. All right. Question. Yeah. How to take advantage of the linearity property? Yeah. So here let me show you how do we take advantage of the linearity property? Yeah. The details. Yeah. All right. So here there is a statement. Yeah. There is a statement here. Any linear combination of two solutions is also a solution. For, let me write the remaining sentence, part of the sentence. For this linear recurrence equation, let me just write equation, okay? Yeah, because even if non-recurrence relation, We can still do that. Okay? So for this linear equation. Okay? All right. So when you have a linear equation, so the meaning of this statement is, when you have a linear equation, if you have two special solutions already, you can use linear combination of that two solutions to form a new solution by that linear combination way. Okay? Yeah. That's the way we take advantage. How we take advantage. So this linear combination way is the commonly used way to take advantage of the linearity property. Yeah. All right. So here let's write our new form of the solution. Yeah. Capital A times the first solution, T1 to the n, that's the first solution, plus capital B times T2 to the n, the second solution. Linear combination of two old special solutions, and by the linearity property, we know this form must be a new solution. Do you agree if we plug in this new form for arbitrary given constant numbers for capital A, capital B, you can get a new solution? Do you agree that? Think about it. Okay? Yeah. So if you plug in this form into the original recurrence relation, can you see the equality still holds, right? Yeah. 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 So if you can see that, yeah, then the next step, how to determine capital A, capital B. Yeah. Because here, capital A, capital B unknown. They're both unknown. Yeah. So we want to determine the values, specific values for capital A and capital B. Yeah. Then the last step, to determine capital A, capital B, we use the initial conditions to determine capital A and capital B. If we get a solution that satisfies initial condition, then we get a Fibonacci numbers. Fibonacci numbers. Because Fibonacci numbers, when we start from the initial conditions, then we do the recurrence relation, we can get a determined sequence of numbers, Fibonacci numbers. Yeah. So here we determine capital A, capital B using the two initial conditions. Yeah. All right. So the goal, determine the coefficients, capital A, capital B, such that initial conditions is satisfied. Yeah. All right. Yeah. Yeah. So here, because here we know this is the solution, right? For any capital A, any capital B numbers, this form is a solution based on our analysis before. Yeah. All right, so now for the initial condition, we have when little n equals 0, let's plug in. So A0 equals A times the parenthesis to the 0, that's 1. Okay? B times parenthesis to the 0, also 1. So A plus B. Yeah. So capital A plus capital B equals 0. Yeah. So you get B equals negative A. That's by first initial condition. So we have second initial condition, so we can find these two values, capital B and capital A. Yeah. All right. So when n equals 1, and let's plug in. Yeah. But this time we replace B by negative A. Yeah. And we know A1 equals 1, second initial condition. Yeah. All right. So after simplification, yeah, because if you replace B by negative A, you can factor that A out, then you do subtraction, you get a root 5 after subtraction. So root 5 times capital A equals 1. So capital A equals 1 over root 5, right? Yeah. So 1 over root 5, and B equals negative A, so B equals negative 1 over root 5. Yeah. Now you go back to our AB form representation for the general solution. Yeah. And this time we know 1 plus root 5 over 2 is golden ratio. Yeah. So, and 1 minus root 5 over 2, it's negative 1 over phi. Negative, yeah, because phi is a positive number. Yeah. So it's a negative 1 over phi. Yeah. And then finally, we plug into the general form, so you get the final representation for the Fibonacci numbers. 1 over root 5, parenthesis, phi to the n minus negative 1 to the n over phi to the n. That's exactly the Fibonacci formula we saw before, and we verified, remember, by the mathematical induction. But here, we solve it. We solve the original recurrence relation to to discover this formula. Yeah. So this is a discovery approach. Yeah. So we took two different approaches. The first time, the verification approach. Second time, discovery approach. Yeah. All right. So that's the complete story. Okay? Yeah. So I hope you can follow this whole story and try to learn something in problem solving. Yeah. Yeah. All right. Yeah. Any question? Yeah. So that's this topic. So we finish this topic. Yeah. All right. Oh, I saw a chat message. Yeah, let me take a look at my chat message. Andy, oh, all right, okay, yeah, cutting out, oh, you're fine, okay, yeah, yeah, I don't know how much, oh, about 15 minutes, oh, is that long? The cutoff is that long, the period? Oh, that's too bad. 15 minutes ago. Oh, that's really bad. Yeah. All right. So, yeah. Okay. Yeah. All right. When I make the video tonight, let me double check it. Yeah. So if I miss some important steps, I may need to record the video, record that part again. Yeah. So I didn't realize, so why the audio has that problem. Yeah. Okay, yeah. All right, so let's continue. Yeah. So let's move to module 4. New module. Yeah. Oh, let me tell you another thing important. Yeah. Yeah. Regarding the module 4. Yeah, because we cannot wait. Before the midterm next week, we have a few classes. Although we will do review sessions, but review sessions only half of the class. Another half we need to learn new materials, module 4 materials. And then for your midterm, midterm, we will not include module 4 in our midterm. So for the midterm, let me write here, midterm content, coverage content, so let me write it clearly here. Okay, module 1, 2, 3, only 3 modules. Okay, will there be review sheet or anything like that study on? So review sheet, no review sheet. No review sheet. Let me tell you how I do the review session. Because because the midterm. So let me tell you the midterm. The midterm questions. The midterm questions comes from 3 quizzes. Quiz 1, 2, 3 plus homework assignment number 1. Okay? All the questions based on our old questions. So basically I modify old questions in some special ways to check your understanding. So if you can, using the appropriate methods, concepts, principles to solve similar problems, not brand new problems, okay? Similar problems in our old assignments. So I will not give you a review sheet. So basically I just explain all the questions in our old assignment in our review sessions. Okay? We allow access quizzes. Right now you can access quiz 1, quiz 2 answers. Not allow access quizzes, and grade will unlock. Unlock. I just unlock quiz 1, quiz 2. Quiz 3 after the deadline, right? Still, this weekend. This weekend after the deadline. So I will unlock quiz 3 answers. So quiz 3. And Monday. Let's say Monday. In our Monday's class, I can talk about quiz 3 questions. Monday's class. Wednesday's class, I will talk about homework assignment solutions because I need to do grading. It will take a few days to do the grading, and the midterm will be given after Wednesday's class. Okay, not in Wednesday's class because it's an online class. Midterm is online. Midterm is online, so we won't do it in our class. So you will do it online. China, admit. Okay, all right, right. So that's about the midterm and the review. Okay, all right. So any questions, just let me know. So I'll move to module 4. Let me look at the time we left. All right. So we have let's say 20-something minutes before the break. So we need to. So we need to start a new topic. Insertion sort. It's a small topic, but very useful. So I try to complete this small topic today. All right. Module 4. All right. How do I here? Good. Okay. No, yeah, color. All right. Yeah, all right. Yeah. Module 4, divide and conquer approach. So this is a very important topic, divide and conquer. Yeah. Part A, insertion sort. Yeah. So in this module, we will learn several basic, important topics. Yeah. All right. So 8.1, insertion operation. Yeah. So we will learn another new sorting algorithm, insertion sort, and it's a simple one. Yeah. So let's start. Yeah. The question, problem 4, revisit. Yeah. So for the solution, so this time the strategy, same old strategy we used before. Okay, start with simple case. Yeah. So we do some experiments. Yeah. So for the experiments, we just try out some relatively simple cases. Yeah. All right. Yeah. So then grow the data size gradually. So at the beginning, let's start with size 1. Yeah. Only one element in the array. Okay. Yeah. All right. So after that, we try 2, 3, and so on. Every time we increase the problem size by 1. Yeah. All right. Then, because every time we add the problem size by 1, then there is a difference part, right? Yeah. Before we add a problem size by 1, and after we add problem size by 1, there is some difference. There is some work we need to do to address the difference of those two subproblems. Okay? Yeah. So that difference part, to take care of that difference part, that's the critical step. Yeah. All right, so let's start to implement this idea. Yeah. Working on the problem size. Yeah. Based on our intuition. Yeah. All right. When we start, our array has only one element, like this one. Yeah. So this represents a one element array. Yeah. And a one element array, it must be sorted, right? Yeah. We do nothing, and we treat it as an ordered array, right? One element already ordered. Yeah. So no comparison to do. We get it sorted. Yeah. All right. Then, next step, because every time we increase the array size by 1, right? How do you grow from one element array to two element array? Yeah. So we assume we add a new element to the one element array. That's the way we grow it. Okay? We grow the array size by 1. Yeah. So we add a new element A1 into our ordered array. So this one we treat as an ordered array. Okay? Yeah. We add it into an ordered array. Right? All right. When we add it into the ordered array, we want to make the new array ordered. After we do some work, we want to make our new array ordered. How many comparisons do you need to make the new array ordered? Yeah. The two element array ordered. Number of comparisons. You need to do comparisons, right? You have to do some comparisons. But the question is, how many comparisons you need to do here? Okay? Yeah. Only one, right? You do one comparison. Yeah. Yeah. So you may argue, because in this case, you may argue, so A1 equal is equal to A0 or not, no matter equal or not, you only need to do one comparison to get it ordered, right? Yeah. So for simplicity, we can assume distinct elements. Yeah. But after we find a solution, we will remove that requirement. Okay? Assumption, distinct assumption. Yeah. All right. So you do one comparison here. Okay? After one comparison, we get this two-element array ordered. Yeah. So this time we assume this new array, two-element array ordered. Yeah. Then grow this two-element array to a three-element array by adding a new element A2. A2. Yeah. This time we need to do a few comparisons and try to put A2 in place. Okay? Try to put A2 in place into an already ordered array. Yeah. It must be at some place, we don't know, but after we do some comparisons, we should know the right position for A2, right? Yeah. So the question, how many comparisons do you need to put A2 in place? For the worst case, yeah, so here, for the worst case, yeah, not the best case, yeah, 2, great, yeah, yeah, array, yeah, perfect, great, that's the answer, yeah. Worst case, 2 comparison, but best case, 1, right? Yeah. So you have best case, you have worst case, yeah, yeah. So best case is 1 comparison, worst case is 2 comparison, yeah, yeah. If I do not say any case, yeah, then you just work on the worst case. Okay, you just work on the worst case. Yeah. All right. Yeah. So 2 comparisons. Yeah. Next one, we can keep doing this. We can keep doing this. Yeah. And we treat the process that we put one new element in place. We treat it as an insertion operation. Yeah. Because it looks like insertion, right? We insert A2 somewhere at the right place in an already ordered array. Yeah. So that's insertion operation. Yeah. Yeah. So then we will study this insertion operation next. Yeah. Insertion operation. Yeah. All right. So here the general case, we insert a new element AK into an ordered array containing k elements. Yeah. So, yeah, this ordered array has k elements. Yeah. So you look at the subscripts from 0 through k minus 1. So there are k elements. All right. Can you tell me when you insert a k into an ordered array with k elements, how many comparisons you need to do? For the general case. This is a general case. Yeah. K could be any number. Yeah. So can you get an answer related to K? Answer related to K. Yeah. How many comparisons? For the worst case. Yeah. Here, K minus 1 or K. Yeah. So here, right, K minus 1 for the worst case. Yeah. Yeah, here. Array here. Remember, as I said, we know there are k elements in the ordered array, right? You have to do comparisons with all of them, right? You cannot miss anyone, right? You have to do comparisons. The new element a sub k, you have to do comparison with all elements in the ordered array. You cannot miss anyone, but the number of elements ordered array is k. Okay? So that means you have to do k comparisons. Yes. Yeah. If you look at your 2 solution before, A2, right? So K equals 2. Your solution is 2, not 1, right? So you can check that. Yeah. Yeah. All right. Yeah. So that's the insertion step. Yeah. So let's move to the next slide. We discuss about this insertion step. Yeah. All right. Insert element in a sorted array at the right position. So that's the insertion operation. Yeah. So let me use a diagram. Yeah, and the K comparison for the worst. Right, exactly. Yeah, K comparison, that's for the worst case. If for the best case, that's 1, right? You only need to compare with the largest element, and we can assume it's greater than the largest element. So best case is 1, always 1. Yeah. But there is an average case. Yeah. Average case somewhere in the middle. Okay? Yeah. You take the average. Yeah. All right. Yeah. So let's move to this slide. Insertion. And we want to look at the details of the insertion step. So here, for the detail, we need to, because when we do the insertion, we need to make a room for the new element, right? We need to make some room for the new element. Yeah. So when we make a room, we need to do shift operations, shift elements. Yeah. So let me use a diagram to show you the insertion operation. Yeah. Shift elements to the right to make a room for the new element. The goal of this step, you need to find a location. You need to put a new element in place. So you need to make some room for the new element. All right, so let's look at this diagram. In this diagram, we want to insert A sub k into somewhere in an ordered array. Yeah. We know the ordered array, they take consecutive locations in main memory, right? How do we store all the elements of an array in main memory? Yeah. So they take consecutive locations in main memory. Okay? Yeah. So after you make the insertion, the elements, the new elements, all the elements in the new array should also take consecutive locations in the main memory. Okay? So you cannot jump. Yeah. So you have to. So for that reason, we need to make room for the new element. Okay? All right. So let me use the diagram to show you how to make room for the new element. All right. Yeah. So suppose the new element is inserted somewhere this place. Okay. Yeah. So here we just do some general discussion. Yeah. That I, the location A sub I plus 1, very general. Okay. Yeah. So let's do the insertion here. Before we do the insertion, yeah, because we consider element A sub k, let's lift this element. Let's copy this element. We lift it. So here I show you. Yeah, I use this, lift step to show you after the lift, this location becomes vacant, right? When it is vacant, we can copy other elements, other elements into this location. But the old element, we lift it. Okay, we lift it. We copy in a temporary location. So lift it. Yeah. Actually, in our final implementation, we do not have to do the same way. Yeah. So here I just here we understand this process. Okay. We understand this insertion operation. We use this way to understand. Okay. All right. So we lift A sub k and make its old location vacant for other elements to be copied into this location. Okay, all right, yeah. So A sub k minus 1 can be copied, can be shifted. Yeah, right shift. Yeah, shift is a copy operation. Okay, shifted to this location. Yeah, yeah, one shift. Okay, if necessary, after we do comparison, if we need, we can shift A sub k minus 2 to its right adjacent location, right? Yeah, because after A sub k minus 1 shifted, this place becomes vacant. Okay? This place, after the shift, it becomes vacant. Okay? And so on. Then another shift. And keep doing shifting operation. Okay? All right, so here, after the shift, now this location becomes vacant, and we assume, we detect this is the right position for the new element. Right position for the new element. Then we just drop it. We copy A sub k into this right position. Okay? Yeah. So think about that. So that's the whole process. Okay? Yeah. So every time when we do one comparison, we know if we should do the shift or not, right? Yeah. If A sub k is less than the current element, then we should do a right shift operation. Shift the current element to the right. Right shift operation. If A sub k is greater or equal to the current element, then we do not do right shift. So we just dropped A sub k to the current vacant location. That process. Okay? Yeah. So that's the how do we do the insertion? How do we do the insertion operation? Yeah. One comparison, and if it is necessary, you do a shift operation, right shift operation, if necessary. Yeah. Sometimes, not necessary, you just drop it to the right location, position. Yeah. All right, so that's the, details of the insertion operation. And think about, if you can do the insertion operation, can you complete the whole sorting algorithm? Yeah. So each step you do this insertion operation. Then from beginning to end, you get the whole array sorted. That's the insertion sort. Yeah, that's the insertion sort. Okay? All right. So that the number of assignments. Yeah. For the number of assignments, we need to look at the best case and the worst case, right? Yeah, the best case and the worst case. Yeah. Yeah. And the average case. Yeah. So here I use the big theta. Yeah. This big theta, you know the meaning of big theta, right? Yeah. So that's for the average case. Constant multiple times k function. Yeah. All right. Yeah. So that's the average case representation. Okay. Yeah. Big theta of k. Yeah. Yeah. So now you know the meaning. So after we learn asymptotic notations, now you know its meaning. Yeah. All right. Yeah. So we complete the insertion sort. Yeah. Next, 8.2, implementation of insertion sort. Yeah. Implementation is quite straightforward. Okay? Yeah. So we just put things together. Yeah. So I think, yeah, so let me look at that. When we put things together at the same time, we can estimate efficiency. Yeah, yeah. Let me finish the slides. We can take a break. Yeah, yeah. Because not much to do here. Yeah. Compare and shift operation. Yeah. So in this diagram, based on this diagram, let's look at the worst case efficiency. Yeah. So each step, the first step, one comparison. For the worst case, second, two comparisons, and so on. The last step, n-1 comparisons. Yeah. When we insert the last element, yeah, n-1 comparisons. Because total elements n, but there is one element to be inserted. Other than that element to be inserted, you only have n-1 elements. So you need to do n-1 comparisons as the last round insertion. So the number of comparisons you need to do, this 1/2 times n-1. This is for the worst case. Yeah. What's the best case? Yeah. Best case, each insertion round, only one comparison. Right? Yeah. Yeah. So here we can write use asymptotic notation, big theta of n squared. Because we ignore the constant. We drop the minor term, and then we ignore the leading constant. So we use this big theta of n squared to represent the category for insertion algorithm. Yeah. All right. Then the best efficiency. The best efficiency, pretty easy. Each round, only one comparison. And how many rounds? n-1 rounds. So equals n-1. Yeah. And we will also like to use the asymptotic notation to represent it. So we drop the minor term. -1 is a minor term. Okay, we drop it. And the leading coefficient, or it's 1. Yeah, so we don't need to do anything for the leading coefficient. So we get the asymptotic notation for the best case of the insertion sort, big theta of n. See? Yeah. Quite different, right? The difference is very big. Big theta of n squared, big theta of n, the difference is huge. N squared and n. That difference is big. Okay? Yeah. So we treat this is the special property of the insertion sort. This property is very useful. Okay, this property is very useful. Yeah. All right. Average case. Yeah. For the average case, yeah, here I skip the details. Yeah. So we know you can calculate. Yeah. Each insertion step you use the average case. Yeah. The 1/2 k. You use the average case as a pretty much just a 1/2 k. Okay. Each step. But this k goes through from 1 through n-1. That's the average case. So you get a big theta of n squared. Okay, yeah. So that's the whole insertion sort. Okay, whole insertion sort. Yeah. All right. Next, we will discuss the application of insertion sort. There is some nice application of insertion sort. All right, so let me stop right here and we take a break. When you come back at 7 o'clock, so we do the review session number 1 for the midterm.